Hi everyone, and welcome to Calculus Chapter 6, Part 3, Limits and L'Hopital's Rule. Okay, we're going to do a quick review of limits and their limit laws because I'm pretty sure you don't remember them. But basically, if you have the limit of a sum, that's the sum of the limits, so you can separate this out, just like you can do with integrals. Okay, number 2, if you have a difference of functions, you can separate it again and do the limits separately and then subtract your results. In number 3, okay, if you have a constant times a function here, you can factor out the constant, do the limit, and then multiply by the constant. 4, if you have a product of functions, you can separate it out and do the product of their limits. And number 5, if you have a quotient of limits, you can do the quotient of the limits. Now, one thing to be aware of is that we really don't use these often in our new lesson, but I wanted to remind you of them because they're things that you've probably forgotten and we do use them occasionally. So let's take a look at some other strategies for evaluating limits. In the first one, I have an example here. They want us to find the limit as x approaches 5 of this quadratic. Now, one thing that I didn't mention in all of these limit laws is that if it's something that's relatively simple to do, if it's a continuous function, usually we can just take this value and put it in for x, and that will give us our limit. So that's what we call the substitution rule. So we can substitute right in that 5, and I get 2 times 5 squared minus 3 times 5 plus 4. And to find that limit, I would just evaluate this. This becomes 50 minus 15 plus 4. Okay, so that becomes, I believe that's 39. 50 minus 15, that's 35, plus 4 is 39, yeah. Okay. This one is another interesting method that we use to simplify limits. So up here, I'm not actually going to do the limit of the top and the limit of the bottom because notice if I put in this 1, I'm going to be dividing by 0 here. I'm going to end up with 0 divided by 0, which is what we call an indeterminate form because you aren't allowed to divide by 0 and this just doesn't work out. Another indeterminate form would be infinity divided by infinity. And we're going to actually focus on those two indeterminate forms today, but let's look at this one first. One of the ways that we can simplify this is by factoring the numerator. X squared minus 1 factors to x minus 1 times x plus 1. Because it is a difference of two squares, notice it's subtracting two squared terms. And then I could simplify this by canceling out the x minus 1's. And then I can just substitute in the value for my limit. So I just put in a 1 here and I get 1 plus 1 is 2. So that is actually this limit. It's approaching 2. So I reduced to get rid of those. Okay, so let's take a look at how limits are seen in what we've been talking about so far in our chapter. We've been talking about e to the x, which is the exponential function with e, and we have also been talking about logarithms and specifically the natural log. Okay, and when I was copying my papers, I think I made a mistake right here. This is just supposed to be an e, not an x. Okay, there we go. Notice e is actually defined as a limit. So the value of e, which is like 2.8 something, is the limit as x approaches 0 of this. Okay, or you can rewrite this as the limit as n approaches infinity of 1 plus 1 over n to the n power. Okay, so actually the number e is defined with a limit, but we can also look at limits from these graphs. So notice in my red graph, as e to the x approaches infinity, as x approaches infinity of this thing, notice e to the x is going to approach positive infinity, because the graph is going up at the rate and it's going to keep going up. So as I go further and further to the right, the graph is headed upward. I'm going to get a positive infinity there. If I do the limit as x approaches negative infinity of e to the x, that means I'm going further and further this way. Notice this graph is approaching 0. That is my horizontal asymptote for this graph. So these can help us with our graphing questions. We won't see those in this, but we have graphed e to the x before. Now let's look at our blue function. We have two limits that we can get from this function. I can do the limit as x approaches positive infinity of the natural log of x. So as I go further and further this way, my natural log of x, although it's not going steeply up like the e to the x was, it will eventually hit infinity. Well, kind of. Infinity is not a number, so it can't really hit it, but it's going to keep going upward. Okay? Now, if I go in this direction, the furthest over it goes is 0. So I can say the limit as x approaches 0 from the positive direction, because notice this graph isn't defined on this side of my my y-axis. The limit as x approaches 0 from the positive direction is negative infinity. I forgot to write my natural log of x. So ln x, negative infinity. There we go. Now we can use those in examples to help us evaluate some limits. So that's another strategy. Okay, so I'm going to keep those up there, and we're going to look at this last example I had. Okay, in the last example, it said find the limit as x approaches positive infinity of e to the 2x over e to the 2x plus 1. Now notice, if I put in infinity, well, we can't really put in infinity, but we can say as x gets really, really big, what's going to happen? Well, the numerator is going to get really, really big, and the denominator is going to get really, really big. This one is not going to really matter. Well, we're not really sure what's going to happen. So let's take a look at how we can simplify this and then see if we can apply some of these limits that we had earlier. So I can simplify the e to the 2x. Okay, so what I'm going to do is divide everything by e to the 2x. I'm just going to reduce my fraction. So the numerator becomes 1. The denominator becomes 1 plus e to the negative 2x. I just reduced the fraction by e to the 2x. E to the 2x divided by e to the 2x is 1. E to the 2x divided by e to the 2x is 1. And 1 divided by e to the 2x is e to the negative 2x. Okay, so that's how I got that. Now I can try my limit again. Okay, the numerator is going to stay a 1, and the denominator is going to grow a lot. So 1 plus 1 over, sorry, it's not going to grow a lot. This is 1 over a very, very large number, which essentially is like 0. So this limit is approaching 0. So I get the limit as x approaches infinity of this thing, e to the 2x over e to the 2x plus 1, is going to be like 1 over 1 plus 0, or just basically 1. And that's my limit there. Okay? Because as x gets really, really big, this thing is going to approach 0 because it's 1 over e to the 2x. And as the denominator gets really, really big, this is approaching 0, and 1 plus 0 is just 1, and 1 over 1 is 1. Okay, let's take a look at one last example. Okay, it's on the back of this one. Okay, we needed to find the limit as x approaches 1 of the natural log of x over x minus 1. Notice what happens. If I try to evaluate this, I get the natural log of 1 over 1 minus 1. Okay? This denominator is 0. From my graph, I know that the natural log of 1 is 0. This is what we call an indeterminate form. Now, I can't actually use the simplifying that I did last time where I factored because, well, this thing can't be factored. So what I'm going to do is use our new rule. And I'm going to save that for the next video. The new rule is L'Hopital's rule, and we'll see that soon.